In this presentation we introduce the concept of electric charge, which is the fundamental quantity of electricity. We start with the basic phenomena related to electric charge and define the electric state of bodies. We discuss the classification introduced by Franklin for the two types of charge found in nature, and interpret the results of some experiment based on the duality of the positive and negative electric charge. Then we talk about electroscopes, which are simple instruments detecting the electric state of bodies, and allow us to determine the type of charge attained by a body. We also present some experiments using such devices to demonstrate the effect of the separation of charge. Based on the results of these experiments, we will define two classes of bodies, called electric conductors and insulators, and discuss the presence of charge in the atoms. Since this opens the way to the corpuscular interpretation of electricity, we will give some remarks on the quantization of charge and present the law of conservation of charge. Then we continue with the famous experiment performed by Coulomb, in which he studied the electric forces acting between charged bodies. We introduce the concept of point charge used to provide a simple description of electric interactions between bodies, and discuss Coulomb's law describing the electric forces acting between point charges as functions of their charge and their distance from each other. We also specify the different units of electric charge used in the CGS and SI system. The choice of the unit for charge determines the unit of the dielectric constant in vacuum, therefore the form of Coulomb's law and other laws of nature related to electricity and magnetism. We finish this presentation with the experiment performed by Cavendish, who attempted to measure electrostatic force with high precision. The result of his measurement demonstrated that the inverse square law of electric force holds, at least with the accuracy achieved in the experiment. We mention other experiment carried out to test the validity of Coulomb's law as well, and show how the results of the measurement become more and more accurate, confirming that the inverse square law holds. We will see that Coulomb's law seems to be valid over large distances, but there are theoretical limitations for the law on subatomic scales. Let us start with a basic phenomenon of electricity called triboelectric effect, and introduce the concept of electric charge. In everyday life, the amber effect, or more generally the triboelectric effect, is a well-known phenomenon. If we rub a piece of amber with wool, then it will attract small objects, for example paper bits. The word electricus was introduced by William Gilbert, an English physician and physicist, who used the term to describe the amber-like property of bodies after the Greek word electron, meaning amber. The triboelectric effect is explained by the presence of electric charge in bodies. When electric charge is present in a body, we say that the body is electrified or it is in a charged state. Our experience also shows that the charged state of bodies remains unaltered in time, and this state is called static electricity. Let us consider two simple experiments demonstrating the basic properties of electric charge in bodies. If we suspend a glass rod through a string or a non-metallic wire and rub it with leather, then the glass rod becomes electrically charged. We can also charge another glass rod by rubbing it with leather and bring near the hanging glass rod. We will see that the two rods repel each other since the hanging rod twists the wire through a given angle, so that the hanging rod turns away from the other one, as the orange arrows show. We can also use ebonite rods instead of the glass rods, but we have to rub them with wool to produce the same effect. The electric charge in each of the rods exerts forces repelling the charge in the other rod, which are indicated with the red arrows. We repeat this experiment, but this time we will bring an ebonite rod near the glass rod suspended through the string. We electrify the hanging glass rod by rubbing it with leather, and we will rub an ebonite rod with wool so that it could also attain charge. If we bring the charged ebonite rod near the charged glass rod, then we will see that the two rods attract each other. That is, the hanging glass rod turns in the direction of the ebonite rod and approaches it. This result demonstrates that the electric charge attained by one of the rod produces a force attracting the charge attained by the other one, and vice versa. We can also perform this experiment several times, when replacing the ebonite rod with other charged bodies. If these bodies are brought near the charged glass rod suspended through a string, they either attract or repel it. This effect is demonstrated when the rod will turn towards or away from the bodies. Then we can conclude from the experiments that electric charge must be different for the glass and the ebonite rods, or generally for two classes of bodies. Benjamin Franklin gave a simple interpretation of this phenomenon. He assumed that there are two types of electric charge, positive and negative. He called the charge of the glass rod rubbed by leather positive, and the charge of the amber or ebonite rod rubbed with wool negative. Based on this interpretation, the experiments show that opposite charges attract each other, while like charges repel each other. If a body is negatively charged, then it repels any negatively charged body and attracts positively charged ones. Similarly, if a body is positively charged, then it repels any positively charged body and attracts the negatively charged ones. If we want to see how the rubbing of bodies helps to electrify bodies, we can make the following simple experiments. Let us charge a glass rod by rubbing it with leather and suspend the charged rod through a string. If we bring the leather near the rubbed glass rod, then the glass rod turns in the direction of the leather, that is, the charged rod and the leather attract each other. Now we can rub the glass rod with leather again and rub an ebonite rod with wool. If we suspend the charged ebonite rod through the string and bring the leather near the rod, then the ebonite rod turns in the direction opposite to the leather, that is, they repel each other. We can conclude from these results that the glass rod attains positive charge and the leather attains negative charge when they are rubbed against each other. In generally, if we rub two bodies against each other which are made of different materials, then the bodies attain the opposite charges. Therefore, the rubbing does not create any charge but separates opposite charges in bodies. Actually, we can check whether the rubbing of bodies is really needed for the separation of charge in them. Let us rub a glass rod with leather and an ebonite rod with fur or wool. Then the glass rod attains positive charge and the ebonite rod attains negative charge, which are represented with the red positive signs and the blue negative signs respectively. If we have two pith balls suspended through strings, though we can touch one of them with the charged glass rod and the other one with the charged ebonite rod. If we remove the rods, we see that the pith balls move towards each other, which indicates that they attract each other. This means there are attractive forces between the pith balls. We can interpret this effect in the following way. When the pith balls are touched with the oppositely charged rods, they obtain positive and negative charges respectively. Then the electric charge can be transferred by contact. Rubbing of the bodies helps us to separate charge in them since it makes the transfer of charge between the bodies more efficient. However, rubbing is not necessary for the separation of charge. We have seen that different materials attain different types of charge, due to contact or friction. Therefore, the behavior of bodies related to the separation of charge depends on their material properties. Let us examine this dependence in the following experiments. If we hold a metal rod in our hand and rub it with wool, then the rod will not attain charge. However, if the metal rod has a glass or plastic handle, then the rod can attain charge after being rubbed with wool. A charged metal rod will lose its charge if we grasp or even touch it with our hand. It is not the case for a charged amber or glass rod. They lose their charge only at that part where they were touched. Based on such a behavior of the different materials, we can divide them into two classes. The first one is the class of conductors, and the second one is the class of insulators. In conductors, electric charge can move and propagate fast. Typical examples for conductors are metals, the human body itself, or simply the ground. Therefore, we can use metal wires to transfer electric charges from a charged body to the ground. As opposed to the conductors, electric charge cannot move in insulators. Such materials are, for example, glass, ebonite, or amber. It is important to note that perfect conductors do not exist. Even if metals are very good conductors, they are not perfect ones. As a result, the border between conductors and insulators is not sharp. We have seen that rubbing bodies against each other brings them into a charged state. In electrostatic, several simple methods have been invented to determine whether a body is in a charged state, that is, whether it attained charge. There are measuring devices called electroscopes, which are able to show the presence of electric charge in bodies. One of the simplest electroscope is the gold leaf electroscope constructed by Abraham Bennett, an English clergyman and physicist in 1787. He used this instrument in many simple experiments, when he studied the basic phenomena of static electricity. In the photo, we can see a gold leaf electroscope with a glass metal case. It consists of a disc called charging plate, which is attached to the top of a vertical metal rod. The rod is normally made of brass, and golden leaves are attached to its lower end. The lower part of the metal rod is encased in the glass metal box insulated from the rod. If a charged body touches the charging plate, then the gold leaves spread apart since the parallel strips with the same type of charge repel each other. The angle between the two golden leaves is proportional to the pair of forces pushing the leaves away from each other. The force is proportional to the amount of electric charge distributed on the surfaces of the leaves. This amount of charge is proportional to the charge transferred from the glass rod, that is the charge of the body touching the plate of the electroscope. The angle between the golden leaves proportional to the original amount of charge of the body. The more the stripes diverge, the greater the amount of the charge in the body is. Then we conclude that the position of the golden leaves in the electroscope indicates the amount of charge of the bodies, which provides a rough measurement of charge. Another type of the electroscopes is the pointer electroscope, which allows us to have a more quantitative description of the amount of charge in bodies. It consists of a charging plate connected to a support stand extending through the center of an insulator scope. A needle rests upon the support stand which can rotate about its pivot. The plate, the stand and the needle are made of a conducting material. If a charged body touches the charging plate, then the support stand and the needle attain like charges and they repel each other. Then the needle will rotate around its pivot until it restores the balance. The rotation angle is proportional to the forces acting between the needle and the support stand. The forces are proportional to the amount of the electric charge distributed on the surfaces of the needle and the stand. This amount of charge is proportional to the charge attained from the glass rod touching the plate. Then we can conclude that the rotation angle of the needle is proportional to the amount of charge attained from the charged body brought in contact with the plate of the electroscope. We can use the golden leaf electroscope to classify different materials as electric conductors or insulators. If we have the same type of electroscopes denoted with the letters A and B, and we charge or electrify the electroscope B, then its gold leaves will spread apart, indicating the presence of charge on the surface of the leaves. Let us connect the charging plates of the electroscopes with a metal wire. Then we will see that the leaves of the electroscope A diverge while the leaves of the electroscope B becomes more relaxed. However, if we connect the charging plates of the electroscopes with a glass rod, then the gold leaves of the electroscopes remain in the same position, indicating that there is no charge transfer between the devices. These experiments demonstrate the following simple facts. In conductors, the charge carriers can move, which allows charge transfer between bodies by using such materials. This was shown in the first experiment, where we could transfer charge between the electroscopes through the metal wire. In insulators, the charge carriers cannot move, which prevents us from transferring charge by using such materials. This could be seen in the second experiment, where the glass rod connecting the charging plates of the electroscopes did not allow the charge to transfer between them. Now let us consider the following experiments demonstrating the transfer of charge between bodies, and presenting how gradual charging of bodies works. We use a simple setup, where a metal ball is hanging on a string. First, we electrify a glass rod so that it could attain charge. Then we touch the metal ball with the charged glass rod, which allows us to transfer some charge from the rod to the ball. This charge transfer can be demonstrated, if we bring the metal ball into contact with the charging plate of an electroscope. We will see that the gold leaves of the electroscope diverge. Since some charge is transferred from the metal ball to the electroscope, the ball lost that amount of charge. We can recharge the metal ball by touching it with the charged glass rod. If we bring the metal ball into contact with the charging plate of the same electroscope again, then the gold leaves of the electroscope rise further. This result indicates that more charge was transferred from the ball to the electroscope, which has an important consequence. With repetition of these steps, we can gradually charge the electroscope, or any other object. By using the same experiment setup, we can also discharge bodies, and demonstrate the neutralization of opposite charges. First, we charge an ebonite rod and touch the charge-free metal ball with it. As a result, we have transferred negative charge from the rod to the ball. Then we bring the metal ball into contact with the charging plate of the electroscope, which was electrified with positive charge from the previous experiment. If the metal ball and the instrument get into contact, then the deflection of the gold leaves will decrease. We can recharge the metal ball by touching it with the charged ebonite rod. If we bring the recharged ball into contact with the charging plate of the electroscope, then the gold leaves become even more relaxed. This result indicates that we remove charge from the electroscope, which is the neutralization of a charged body. By repeating this process several times, we can gradually discharge the electroscope or any charged object. We can also use the electroscope in the experiments, where we study the separation of opposite charges by friction. If we rub a paraffin wax bar against the charging plate of an electroscope, and remove the paraffin wax bar from the plate, then the gold leaves of the electroscope will rise. If we touch the charging plate with the paraffin wax bar again, the gold leaves will relax. We can interpret this result in the following way. The same amount of positive and negative charges are separated in the bar in the electroscope by rubbing them against each other. Then the same amount of positive and negative charges are neutralized in the bar in the electroscope by bringing them into contact with each other again. We have already seen that we can separate positive and negative charges in bodies if we rub them against each other. Now we can ask what will happen if we just bring the charged bodies near the electroscope. In the first experiment we use a positively charged electroscope, where the separated gold leaves indicates the positive surface charge on the leaves. If we bring a positively charged glass rod near the charging plate of the electroscope, then the gold leaves rise further. If we remove the rod from the vicinity of the plate, the gold leaves take their original position. In the second experiment we can also bring a negatively charged ebonite rod near the charging plate of the positively charged electroscope. Then the gold leaves of the electroscope become more relaxed. If we remove the rod from the vicinity of the plate, the gold leaves rise to their original positions. The interpretation of these results is the following. If two charged bodies only approach each other, then the charge separation can already be measured in the bodies. In the first experiment the positive charges repel each other in the bar and the electroscope, reducing the surface charge on the plate of the measuring device and increasing it on the gold leaves. In the second experiment, the negative and positive charges in the bar and the electroscope attract each other, increasing the surface charge on the plate of the electroscope and decreasing it on the gold leaves. Therefore, we can determine the type of charge in a body without bringing it into contact with the electroscope. Let us study the separation of the positive and negative charges in greater detail. If we rub bodies against each other, we can separate the positive charge from the negative one in bodies. As already mentioned, the friction between the surfaces of the bodies helps the separation. However, this separation can be done by the effect of separation of charge without bringing the bodies into contact. This effect will be demonstrated in the following experiment. We use two electrically neutral metal cylinders denoted by A and B, which are brought into contact with each other. Both cylinders are mounted on stands made of some insulating material. First we bring a negatively charged ebonite rod near the cylinder A, and move the cylinders away from each other while we keep the ebonite rod close to the cylinder A. Then we remove the ebonite rod and determine the types of charge in the cylinders with an electroscope. We find that the cylinder A has positive charge and the cylinder B has -1. This effect is the separation of charge in the two cylinders. After having brought the charged cylinders into contact with each other, we find that the cylinders become electrically neutral again. We can give the following explanation for the separation of charge demonstrated in this experiment. In the natural electric state, conductors contain the same amount of positive and negative charges, which are evenly distributed in the conducting body. As a result, the entire conductor is electrically neutral. In the vicinity of a charged body, there is a charge separation in the conductor. If a body near the conductor has negative charge, then this charge attracts the positive charge and repels the negative one in the conductor. In the part of conducting material that is close to the negatively charged body, the positive charge will be abundant. On the opposite side of the conductor, there will be an excess in the negative charge. This is the effect of the charge separation in a conductor. If we remove the charged body from the vicinity of the conductor, then the even distribution of charge will be restored in the conducting material and becomes electrically neutral. The electric charge induced by the separation of charge is called induced electric charge. Let us consider the following experiment related to the induced charge and the concept of ground in electrostatics. In this experiment setup, we use a grounded metal cylinder, that is a conducting body connected with the ground through a metal wire. First, we bring a negatively charged ebonite rod near the grounded metal cylinder. If we remove the ebonite rod and disconnect the cylinder from the ground, we find that the cylinder is positively charged. The explanation of this result is simple. The negatively charged ebonite rod brought near the cylinder attracts the positive charge and repels the negative one in the conducting body. The left-hand side of the cylinder is closer to the rod and it will be abundant in induced positive charge. The right-hand side is far from the rod and it will attain more induced negative charge. Since the right-hand side of the cylinder is connected to the ground, negative charge flows from the cylinder to the ground through the wire. The charge transfer causes shortage in the negative charge in the cylinder. If we remove the ebonite rod and disconnect the ground, the separation of charge will cease in the cylinder and the charge becomes evenly distributed in it. Since some amount of negative charge was already removed from the cylinder, its net charge will be positive. This experiment demonstrates that the ground or the earth behaves as an electric reservoir with a vast capacity. Theoretically, it can attain or supply an infinite amount of charge without being in a charged state. As a result, we can transfer an arbitrary amount of negative or positive charge between any object and the ground if we bring them into contact. The photo shows a building grounded to the earth for safety reason. Since the capacity of the ground is huge, it can be used to dissipate the great amount of charge from the lightning strike through the lightning rod connected to the ground. This application demonstrates that the grounding system of the Earth provides a good protection of any device from electric shocks. The ground symbol indicates on any instrument or any object that it is grounded or connected to the grounding system. Now, let us discuss the modern interpretation of the phenomenon of electricity based on atomic physics. This interpretation provides us deeper knowledge on the relation between electric charge and matter. In modern physics, electric charge is a basic property of the atoms, molecules and elementary particles such as electrons, protons and neutrons. The atoms and molecules are electrically neutral due to their structural properties. The ionization of atoms and molecules modifies their electron shells and transforms them into ions, which are charged particles. What are the properties of electric charge in such a model? Electric charge, like mass and energy, is quantized. Any macroscopic charge Q is given by an integer multiple of the electric charge carried by a single electron called the elementary charge E. We can write the charge Q as plus minus n times E, where n is an arbitrary integer number and the signs plus and minus indicate whether the charge is positive or negative. Since the elementary charge E is tiny, every macroscopic charge Q consists of an extremely large number of elementary charges. This important fact allows us to regard the macroscopic charge as a continuous quantity. We saw that the electron has a negative elementary charge, which we can denote with minus E, the proton has a positive elementary charge, denoted by plus E, and the neutron has no electric charge, that is, the neutron electrically neutral. Therefore, electrons and protons carry opposite charges with the same magnitude. We also call the charged particles charge carriers. As a result, electrons repel each other with their like charges, so do protons. However, electrons and protons attract each other with their opposite charges. Since the particles in atoms carry charges, the question is how electric charge is distributed in atoms. In the atom model of matter, the atoms are the building blocks of matter which determine the structural properties of the elements. The atoms have two parts, the nucleus and the electron cloud or shells. The nucleus of an atom consists of the same number of protons and neutrons, although their numbers differ in isotopes. The average radius of a nucleon is measured from about 1 to 7 times 10 to minus 15 meters. The electron cloud is located around the nucleus and its diameter is about 1 to 3 times 10 to minus 10 meters. Since the number of protons and electrons is the same in an atom, it has the same amount of positive and negative charges. As a result, atoms are electrically neutral. There is an electrostatic attraction between the positively charged nucleus and the negatively charged electron shell. There is also a repulsion between the electrons in the shell. Such repulsion exists between protons in the tightly packed nucleus as well, but the attraction due to nuclear forces is much more stronger, which keeps these particles together. Due to ionization, atoms losing or capturing electrons become positively or negatively charged ions. Electrons, charged ions or other charged particles are called charge carriers. In solids the situation is more complicated since the nuclei of the atoms have fixed locations, whereas the electrons can move in these materials. In the case of metals, the valence electrons can freely propagate between the atoms. When the valence electrons leave their atoms, the atoms become charged ions. In insulators and dielectric materials, the electrons have a very limited motion. Since the displacements of the valence electrons is limited, their atoms can only be polarized and become electric dipoles. If we use the model based on atom physics, then we can provide a corpuscular interpretation of the static electricity in matter. According to this model, during the friction of two electrically neutral bodies made from different materials, the charge carriers migrate from one material into the other one. In this example, the charge carriers are electrons and they migrate from the wool into the ebonite. After the separation of charge, the body capturing electrons becomes positively charged, whereas the body losing them becomes positively charged. Therefore, the wool and the ebonite rod attain positive and negative charges respectively. We note that the number of electrons captured by the ebonite rod is equal to the number of electrons migrated from the wool. In the experiment with the metal cylinders, we brought a negatively charged ebonite rod near the cylinder A. Then the corpuscular explanation of the separation of charge is the following. The negatively charged ebonite rod repels the free electrons in the cylinder A, which results in a shortage of electrons in it. At the same time, there is an excess of electrons in the cylinder B, since it is in contact with the cylinder A. As a result, the cylinders A and B attain positive and negative charges respectively. If we separate the two cylinders, then the positive charge remains in the cylinder A and the negative one remains in the cylinder B. That is, we have induced charges in the cylinders. If we bring the cylinders into contact again, then they become electrically neutral, which shows that the two cylinders have the same amount of the induced charges. The corpuscular interpretation also helps us to understand the transfer of charge from bodies to the ground. If we bring a negatively charged ebonite rod near a grounded metal cylinder, the negative charge on the rod repels the free electrons in the cylinder. These repelled free electrons will flow into the ground through the metal wire connecting it with the cylinder. As a result, there will be a shortage of electrons in the metal cylinder, which becomes positively charged. If we remove the ebonite rod and disconnect the cylinder from the ground, the positive charge on the cylinder can be measured by an electroscope. If a positively charged glass rod is brought near the grounded metal cylinder, then the positive charge on the rod will attract the free electrons in the cylinder. Free electrons also flows into the cylinder from the ground through the metal wire. As a result, there will be an excess of electrons in the metal cylinder, which becomes negatively charged. If we remove the glass rod and disconnect the cylinder from the ground, then the negative charge on the cylinder can be measured by an electroscope. We can also ask what happens to the electroscope in these experiments in the light of the corpuscular theory. If an electrically charged body is brought near the charging plate of the electroscope, then both negative and positive charges are induced in the measuring device due to the separation of charge. The charging plate and the gold leaves attain opposite charges. If we use a positively charged glass rod, then the plate becomes negatively charged and the leaves attain positive charge. If we use a negatively charged ebonite rod, then the plate becomes positively charged and the leaves attain negative charge. Since like charges on the two gold leaves repel each other, the leaves will diverge. If we remove the charged body from the vicinity of the charging plate, the gold leaves relax. That is, the instrument has no longer induced charge. If a charged body is brought into contact with the charging plate of the electroscope, then charge carriers are transferred from the body to the instrument and it will attain the same type of charge. In the experiments presented here, we could use an electroscope to determine the type of the charge attained by a body. It is very simple to perform such measurement if we prepare the electroscope, that is, if we use a charged instrument. Let us suppose that the electroscope we use have negative charge. Then its gold leaves diverge, since the like charges on the leaves repel each other. If we bring a negatively charged ebonite rod near the charging plate of the electroscope, the gold leaves of the electroscope will rise more. Generally, if we bring a body with like charge near the plate of the charged electroscope, then the gold leaves of the electroscope will diverge more. We can explain this result based on the corpuscular theory. Due to the induced charges in the electroscope, the amount of the negative charge carriers increases on the leaves. But we also know that the more charge carriers on the gold leaves are, the greater the repelling force between the stripes is. Therefore the leaves rise further. Now we can bring a positively charged glass rod near the plate of the negatively charged electroscope, and we find that the gold leaves become more relaxed. Generally, if we bring a body with opposite charge near the plate of the charged electroscope, then the gold leaves of the electroscope will become more relaxed. Due to the induced charges in the electroscope, the amount of the negative charge carriers decreases on the leaves. The fewer the charge carriers on the gold leaves are, the less the repelling force between the stripes is. The experiments presented here also demonstrate the conservation of electric charge. If we rub electrically neutral bodies against each other, then the excess of electrons in any of these bodies is equal to the shortage of the electrons in the other one. That is, the induced charges in both bodies are equal to each other. For example, if we rub an electrically neutral ebonite rod with wool, then free electrons move from the wool into the ebonite rod. If we remove the wool, then the wool attains positive charge and the ebonite rod attains -1. If we touch the charged ebonite rod with the charged wool, then they become electrically neutral again, demonstrating that the wool and the ebonite rod have the same amount of induced charge. This result could also be seen in the experiments, where charged bodies produce the separation of charge in the bodies brought near them. We can remember the experiment with the metal cylinders as well, where we brought a negatively charged ebonite rod near the electrically neutral metal cylinders A and B kept in contact with each other. We could demonstrate the charge separation in the cylinders when we separated them, and remove the charged ebonite rod from the vicinity of the cylinder. The cylinders A and B attained positive and negative charge respectively. When we brought the cylinders into contact with each other, both of them became electrically neutral. Therefore, the excess of electrons in the cylinder B was the same as the shortage of them in the cylinder A. This result shows that the two cylinders have the same amount of induced charge. Other important examples in atom physics are the electron-positron pair creation and annihilation. When an electron with a charge -e and a positron with a charge +e collide at low energy, the process results in the annihilation of both the particles and in the creation of two gamma photons. During the destruction of the electron and the positron, the charges -e and +e disappear, and electrically neutral gamma photons are emitted. On other hand, a gamma photon near a nucleus can also disappear while an electron-positron pair is produced. Both examples demonstrate the conservation of charge in the annihilation and creation of charged particles. All these phenomena verify the law of conservation of electric charge, which states that the net charge, that is the algebraic sum of the charges, is constant in any electrically isolated system. We also note that electric charge is relativistically invariant, that is, the amount of charge is the same in any frame of reference, no matter if the frame is at rest or in motion. Therefore, the amount of the electric charge remains the same whether its carrier is moving or not, and it does not depend on the velocity of its carrier. Given positive or negative charge, carriers at rest will still have the same charge when they are in motion. It is easy to see if the amount of charge depended on the velocity of its carrier, then we could change the amount of the net charge in an electrically isolated system by accelerating a given type of charge in the system. In the previous experiments we have seen that charged bodies attract or repel each other, indicating the presence of forces between them. Now we can discuss Coulomb's law, which determines the forces acting between point-like charged bodies. The point-like charged body is an idealized model of an electrically charged body with a size or extension that is negligible with respect to the distances between the body and other charged bodies considered in the problem. A point-like charged body is normally called a point charge or a charged particle. Charles Augustin de Coulomb, an army engineer and physicist, gave the first quantitative description of the attractive and repulsive forces exerted by electrically charged bodies on each other. In his famous experiment, he determined the force acting between two small electrically charged spheres. Coulomb built a torsion balance apparatus to measure the electric forces. He used a suspension head and attached a string to it, which was hanging in a metal column and ended inside a glass cylinder. Coulomb suspended the metal sphere S1 with a balanced crossbar through the string, and attached a paper scale to the glass cylinder to measure the angular position of the sphere. He also placed the metal sphere S2 in the glass cylinder, which had a fixed position with the distance r from the metal sphere S1. Coulomb charged the small metal spheres S1 and S2 with the positive charges Q1 and Q2. Then the metal spheres repelled each other, and the sphere S1 attached to the crossbar turned away from the sphere S2. He turned the suspension head in the opposite direction, so that the sphere S1 was moved back to its original position. In the new balance, the torque of the repelling force between the spheres was equal to the torque due to the torsion of the string. The rotation angle of the suspension head, the lever arm of the crossbar, and the torque of the string determine the force acting between the spheres. By performing this experiment, he could determine the electric forces acting between the charged spheres S1 and S2 with different distances between them. If the diameters d1 and d2 of the spheres S1 and S2 are negligible to the distance r between the spheres, then the charged spheres can be regarded as the point charges Q1 and Q2. The position vector pointing from the point charge Q2 to the point charge Q1 is denoted by the bold letter R. Here the force F12 is the force exerted on the point charge Q1 by the point charge Q2. Similarly, the force F21 is the force exerted on the point charge Q2 by the point charge Q1. Since Q1 and Q2 are like charges, these are repelling forces. Coulomb measured the rotation angle of the torsion head as a function of the distance r between the spheres for given charges Q1 and Q2, and he found that it is inversely proportional of the square of the distance. The plot shows the result of a typical measurement, where the data points scatter around a graph of the function r to the power of alpha, where alpha is equal to -2. This is an inverse square power law. Since the rotation angle is proportional to the electric force acting between the point charges, we can conclude that the magnitude F of the force measured between the point charges Q1 and Q2 is proportional to the inverse square of the distance r between them, for given charges Q1 and Q2. Coulomb also determined the forces for different amounts of charges Q1 and Q2 attained by the spheres S1 and S2, while the distance r was fixed between them. It was a more challenging task, since no instruments were available at that time which could allow him to measure the amount of charge with a high accuracy. In order to solve this problem, Coulomb used metal spheres with exactly the same size. He could electrify a metal sphere with an arbitrary amount of charge, let us say Q, and he brought it into contact with an electrically neutral metal sphere. Then some amount of charge could be transferred from to the neutral sphere and both of the spheres become charged. Based on symmetry considerations, he concluded that the half of the charge Q remained on one of the spheres and the other half of it was transferred to the other one when he disconnected them. As a result, he could have the amount of charge of the original metal sphere. He brought the metal sphere with the half of charge Q into contact with the neutralized metal sphere again and have its charge. By repeating this method he was able to produce of a series of charged spheres with the amount of charges Q, the half of Q, the fourth of Q, the eighth of Q, and so on. He carried out the experiment with this series of charges, and he found that the force acting on the point-like charges Q1 and Q2 is proportional to the product of the amounts Q1 and Q2 of the charges for a fixed distance between them. Coulomb performed his experiments with both like charges where the spheres repelled each other, and opposite charges where the spheres attracted each other. Based on these results he formulated the law, which we call Coulomb's law today. This law states that the force acting between two charged particles is proportional to the product of the amount of their charges, and inversely proportional to the square of the distance between them. In the formula we see that the force exerted on the point charge Q1 by the point charge Q2 is equal to Q1 times Q2 over the square of the distance r, and it acts in the direction of the vector r pointing from the point charge Q2 to the point charge Q1 for like charges, and acts in the opposite direction for opposite charges. The proportionality factor between the force and the quantities in the right-hand side is denoted by K. By virtue of the law of action and reaction, the force exerted on the point charge Q1 by the point charge Q2 is equal to the force exerted on the point charge Q2 by the point charge Q1, and acts in the opposite direction. That is, F12 is equal to minus F21. The orientations of the force vectors are determined by the signs of the charges Q1 and Q2 in the formula, like charges repel each other, and opposite charges attract each other. The only quantity, which has not been clarified in Coulomb's law, is the proportionality constant K. However, this multiplicative factor depends on which system of units is chosen to define the unit of charge. In Coulomb's law, there are two other quantities besides charge, the force F and the distance r. The units of force and distance or length are fixed in mechanics. The unit of force is equal to the unit of mass denoted by m, times the unit of length denoted by L, times the unit of time denoted by t raised to the power of minus 2. The most frequently used systems of units are the CGS system and the SI system. In the CGS system, the units of the fundamental quantities length, mass and time are centimeter, gram and second, respectively. In the SI system, these fundamental units are meter, kilogram and second. If we use the CGS system, then the unit of force is gram times centimeter over second squared, which is called dyne and its symbol is dyn. This unit together with the one of length can be seen in the table. If we use the SI system, then the unit of force is kilogram times meter over second squared, which is called newton, where length is measured in meters. As a result, we can state the following. We can choose the unit of charge in such a way so that the proportionality factor K becomes a dimensionless quantity which is equal to 1. By virtue of Coulomb's law, the unit of force is equal to the ratio of the square of the unit of charge to the square of the unit of distance. In the CGS system we can write that gram times centimeter per second square is equal to the ratio of the square of the unit of charge to centimeter square. Then the square of the unit of charge is equal to gram times cubic centimeter per second squared. This expression defines the electrostatic unit of charge, abbreviated as ESU, where 1 CGS electrostatic unit of charge is equal to 1 centimeter to 3/2, times gram to the power of half, times second to minus 1. The interpretation of the electrostatic unit is then the following. 1 ESU of charge placed 1 centimeter from a similar charge in vacuum will repel it with a force of 1 dyne. The elementary charge measured in CGS ESU is about 4.8 times 10 to minus 10 ESU. We see from its definition that the CGS electrostatic unit of charge is based on Coulomb's law and the interaction between static charges. Besides the electrostatic unit, we also use the CGS electromagnetic unit of charge abbreviated as EMU, which is based on the interaction between parallel, infinitely long wires carrying charge. Various unit systems can use both electrostatic and electromagnetic units. In the case of Gaussian CGS units, quantities of electricity are the same as those in the CGS electrostatic units, whereas quantities of magnetism are the same as those in electromagnetic CGS units. Like the CGS electromagnetic unit of charge, the SI unit of charge is based on the interaction between wires carrying charge and on the natural laws describing this interaction. The SI unit of charge is named after Coulomb and denoted with C. The definition of 1 Coulomb is the following. 1 Coulomb is the amount of charge carried by a current of 1 ampere flowing for 1 second. Since we have not defined ampere, the unit of the amount of the electric current yet, we express Coulomb in the terms of the elementary charge. 1 Coulomb corresponds about 2.979 times 10 to 9 electrostatic units, or approximately 3 times 10 to 9 ESU. Conversely, the elementary charge is about 1.6 times 10 to minus 19 Coulomb. If force, distance and charge are measured in SI units, then the proportionality factor K, called Coulomb constant, is equal to about 9.98755 times 10 to 9 Newton square meter per Coulomb squared. Since the SI system has some advantages, we will use SI units. Firstly, the SI system is coherent, since all its units are obtained from the fundamental units by multiplication or division. Secondly, the SI system is rational, that is, it assigns only one unit to a given quantity, for example to the different types of energy, like mechanical, chemical or electrical energy. Lastly, the SI system is absolute, which means it does not contain gravitational units, that is, the gravitational acceleration g is eliminated from the formulae. Many formulae in electrodynamics contain the multiplicative factors 4 pi and c, that is the speed of light in vacuum. The SI system, being rational, assumes that we can define the Coulomb constant K in the terms of the dielectric constant of vacuum or vacuum permittivity. That is, K can be given by 1 over 4 pi epsilon naught, where epsilon naught denotes the dielectric constant in vacuum. Then the rationalized form of Coulomb's law contains the multiplicative factor 1 over 4 pi epsilon naught. The value of vacuum permittivity can be determined by the expression of the Coulomb constant, which is approximately 9 times 10 to 9 Newton square meter per Coulomb squared. If we substitute this value into the expression of the equation for the Coulomb constant, we can express epsilon naught from the result. Then we obtain about 8.85 times 10 to minus 12 Coulomb squared per Newton square meter for the dielectric constant in vacuum. There is also a relationship between vacuum permittivity and the speed of light c in vacuum, namely, epsilon naught is equal to 1 over 4 pi times 10 to minus 7 times c squared. In fact, this relation indicates that the effects measured in the experiments determining the value of the Coulomb constant are related to the propagation of light, that is, the electromagnetic radiation. We have seen that Coulomb's law determines the force exerted on a point charge by another one. The principle of superposition of forces is related to a more general situation, where more than one point charges exert forces on a point charge. This principle was introduced in mechanics for forces of any kind, and we can also apply it to electric forces. Then it claims that the effect on a point charge produced by a system of point charges is equal to the net effect on the given charge produced by all the other individual charges in the system. In other words, the principle of superposition of forces tells us that the force between any pair of point charges is given by Coulomb's law, regardless of the presence of the other point charges in the system. We can illustrate this principle with the following example. Let us consider the system of charges Q1, Q2, Q3, ellipsis, Qi, ellipsis Qn. For the sake of simplicity, we also assume that the system of n-point charges consists of like charges, that is, all the forces are repulsive in the system. This restriction just determines the direction of the forces acting between the charges, which makes easier to depict them in the figure. In the general case, the calculation of forces is the same, but the figure becomes more complicated. Now we calculate the forces acting on each point charge step by step. First, we calculate the force F1 acting on the point charge Q1. This is the net force of the forces exerted by the point charges from Q2 to Qn. We start to sum up these forces with the force F12, which is exerted by the charge Q2. Its direction is determined by the direction vector R12 pointing from the charge Q2 to the charge Q1. Its magnitude depends on the charges Q1 and Q2 and the length of the vector R12. Similarly, the force F13 is exerted by the charge Q3 with the direction determined by the vector R13, and the magnitude depending on the charges Q1 and Q2 and the length of the vector R13. We can continue the sum through the forces F1I exerted by a general point charge Qi in the system, where I is not equal to 1. These forces are always determined by the charge pairs Q1 and Qi and the length of the vectors R1I. The last term of the sum will be the force F1n exerted by the charge Qn. In the next step, we compute the force F2 acting on the charge Q2, which is the sum with the force F21 exerted by the charge Q1, the force F23 exerted by the charge Q3 and so on. A general term in this sum is the force F2I exerted by the point charge Qi, and this sum finishes with the force F2n exerted by the charge Qn. In the third step we can compute the force F3 acting on the charge Q3, where we sum the forces up from the force F3(1) exerted by the charge Q1, through the force F3(2) exerted by the charge Q2, and so on. In general, we sum up the forces through the force F3I exerted by the point charge Qi, where I is not equal to 3, and the last force in the sum is force F3n exerted by the charge Qn. We can continue the calculation of forces up to the force acting on the point charge Qn. Here we see that the forces F1, F2, F3 and so on are the vector sums of n-1 forces. That is, each net force acting on a given charge can be calculated by applying the parallelogram law for the vectors in the sum. For example, let us consider the point charge Q1, where the first force in the sum is the force F12 exerted by the point charge Q2, and the second one is the force F13 exerted by the point charge Q3. By applying the parallelogram law, we obtain the net force of these forces. Then we take the next force in the sum, which is the force F14 exerted by the point charge Q4, and apply the parallelogram law for the net force and the force F14. This operation gives a new net force, and we can continue the calculation with it and the rest of the forces in the sum. We need to perform the same steps for calculating the net force F2 acting on the point charge Q2, the net force F3 acting on the point charge Q3 and so on. This procedure illustrates how we can apply the principle of superposition of Coulomb forces. The force Fi exerted on the point charge Qi by all the other n-1 point charges in the system is equal to the sum of Fij, where the index j runs from 1 to n and j is not equal to I. The force Fij is the force exerted on the point charge Qi by the point charge Qj, regardless of the presence of the n-2 point charges in the system, and it is given by Coulomb's law. That is, Fij is equal to 1 over 4 pi epsilon naught, times the ratio of Qi times Qj to Rij squared, times the vector Rij divided by its length. If we compare Coulomb's law with Newton's law of gravitation, we can see that they look similar. Newton's law of gravitation determines the gravitational force between bodies. Let us consider two bodies, for example two spheres with the masses m1 and m2 respectively. If their radii d1 and d2 are small compared to the distance are between the spheres, then we can regard them as point masses in the study of the gravitational interaction between them. Newton's law states that the gravitational force F12 exerted on the point mass m1 by the point mass m2 is given by the gravitational constant gamma, times the ratio of the mass m1 times the mass m2 to the square of the distance r, times the distance vector r divided by its length. The force F21 is just the opposite of the force F12, that is, F21 is equal to minus F12. Although Coulomb's law and Newton's law look similar, there are important differences between electric and gravitational forces. If we compare the two interactions, we find that in the case of Newton's law of gravitation, there exists only one type of mass which is the source of the gravitational field, whereas in the case of Coulomb law, there exist two types of charge, positive and negative. Based on this difference, gravitation is always an attractive force, whereas the electrostatic force can be attractive or repulsive depending on the types of charges present in the interaction. A third important difference between the electrostatic and the gravitational forces is their magnitudes. The magnitude of the Coulomb force is extremely different from the one of the gravitational force in Newton's law. If we compute the ratio of the magnitudes for the two types of force in the case of two interacting electrons, we can write that this ratio is equal to the ratio of the square of the elementary charge E divided by 4 pi epsilon naught, to gamma times the square of the electron mass me. If we substitute the numerical values into all the natural constants, we obtain 4.26 times 10 to 42. The ratio of magnitude the electrostatic force to gravitational force has a smaller value in the case of the interaction of an electron and a proton. Although protons have the same charge as electrons, they are much more massive particles. As a result, the ratio of the magnitude of the forces is equal to 2.27 times 10 to 39. These results demonstrate that gravitational forces are negligible compared to electrostatic forces on the scale of atoms, molecules and nuclei. However, gravitational force on a cosmic scale dominates interactions between large objects such as planets, stars and galaxies because it is always attractive, while Coulomb forces on average tend to cancel. As mentioned earlier, Coulomb faced some challenges when we performed his experiment with the charged metal balls attached to a torsion balance. The maximum accuracy can be achieved with a torsion balance in such experiments is about 2%. However, instead of the direct measurement of force there is a much more accurate method to demonstrate Coulomb's law, that is the electrostatic force is inversely proportional to the square of the distance. This method is based on the fact that there is no electric force inside a spherical shell with a homogeneous charge distribution. The absence of electric forces inside such a shell can be proven by applying simple geometric principles. These principles were originally presented by Newton in his Principia for the proof of the absence of gravitational forces inside a massive spherical shell. They go as follows. Let this circle represent the cross-section of the charged spherical shell with the center O. If there is a small point charge in an arbitrary point P inside the shell, then we can compute the electric forces exerted on this test charge by the charged shell. First, we examine the effect of a given charged surface area around an arbitrary point P1 on the shell. The points P and P1 also determine a line intersecting the shell and the point P2. The surface area of the point P1 is subtended its solid angle from the apex and the point P. By definition, the solid angle omega is given by the ratio of the projected surface area AP to the square of the distance r of the surface from the apex. The projected area AP is the amount of the area A seen from the apex. Then it is equal to the area A times the cosine alpha, where alpha is the angle measured between the surface normal and the direction of the surface area seen from the apex. We choose the infinitesimal area element dA1 around the point P1 on the spherical shell, which is subtended the solid angle element d omega. Then d omega is given by the ratio of dA1 times cosine alpha to r1 squared, where r1 is the distance between the point P1 and the apex P. Here the angle alpha is measured between the directions of the segments OP1 and PP1. We can also consider the area element dA2 around the point P2, which is subtended the same solid angle d omega. Therefore, d omega is equal to dA2 times cosine alpha divided by r2 squared, where r2 is the distance between the apex P and the point P2. The angle alpha is measured between the directions of the segments OP2 and PP2, which is the same angle as the one measuring the inclination of the surface area in the point P1. Then we can write that the ratio of dA1 to r1 squared is equal to the ratio of dA2 to r2 squared. Now we can examine the electric forces F1 and F2 exerted on the small point charge in the point P by the charge distributed over the area elements dA1 and dA2. Here we assume that the charges on the shell and in the point P are like charges and the forces are repulsive between them. Since the spherical shell is homogeneously charged, the amount of charge over a given surface area on the shell is proportional to the surface area itself. If Coulomb's law or the inverse square law is valid, then the force F1 is proportional to the amount of charge distributed over the area element dA1 divided by the square of the distance r1. That is, the force F1 is proportional to the area element dA1 divided by r1 squared. Similarly, the force F2 is proportional to the ratio of dA2 to r2 squared. But we have already seen that the ratios in the right-hand side of these expressions are equal due to symmetry of the setup. Therefore, the forces F1 and F2 have the same magnitude but the opposite direction. As a result, the net electric force exerted on any charge in the point P by the charge distributed over the area elements dA1 and dA2 vanishes. Since the point P1 was arbitrary, we can choose any other point on the spherical shell and we obtain the same result. Each charged area element on the shell has its own contribution to the forces acting on any charge in the point P. But at the same time, each area element has its corresponding charged area element on the other side of the point P, which produces an electric force with the same amplitude in the opposite direction. Therefore these forces cancel out. We can conclude that the net electric force exerted on the test charge in the point P by the total amount of charge homogeneously distributed over the whole spherical shell is zero. Since the point P was an arbitrary point inside the shell, this must hold for all the interior points. Then we have proven that there are no electric forces inside a homogeneously charged spherical shell, if the inverse square law holds for them. Based on this theorem proven by Newton, Henry Cavendish was able to demonstrate the inverse square law for electrostatic force about 14 years before Coulomb, but he never published the results of his experiment. He constructed a simple apparatus, which can be seen in the photo and the figure. The main parts of the apparatus are two hemispherical shells around an inner globe, which does not touch them. The hemispheres are attached to a hinged wooden frame and they can be brought together by closing the frame. The inner globe is suspended, using the support of the insulating frame. The hemispheres and the inner globe are covered with metal foil, and they are connected with a conducting wire. Both conductors are initially uncharged. In the experiment, Cavendish electrified the outer sphere, then he cut the wire by means of a silk thread and opened the frame. The charge of the inner globe was measured by a pair of pith ball brought against the globe. If the outer hemispheres produced interior electric forces, then charge would naturally migrate to the inner globe. However, Cavendish found that the pith balls he used for the measurement did not separate, showing that the inner globe did not attain any charge. That is, no electric force could be detected inside the charged hemispheres, and Cavendish concluded that the electric force obeys the inverse square law of distance. We can specify the accuracy of the measurement by determining the maximal possible deviation of the measured data from the inverse square law. The magnitude of the electric force between point charges must be proportional to 1 over the distance r raised to the power of 2 plus delta, where r is the distance between the point charges and the deviation delta gives the limit of the accuracy of the measurement. By performing his experiment in 1773, Cavendish concluded that the negative exponent in the force law could not differ from 2 by more than about 1/50th, as shown in this table. In fact, this result was reported by Maxwell, who discovered Cavendish unpublished results 100 years after he recorded them. Maxwell and his student performed their own version of Cavendish's experiment in 1873, and they could reduce the uncertainty of the measurement to 1/21,600th. In the last century, several tests had been carried out confirming the validity of the inverse square law for electric forces with higher and higher accuracy. In 1938, Plimpton and Lawton repeated the test by placing a very sensitive measuring equipment in the concentric metal globes, and they were able to reduce the value of delta to 2 times 10 to minus 9. A relatively new experimental test was performed by Williams, Fowler and Hill in 1971. They used an apparatus with 5 concentric conductors, which allowed them to have precise corrections in the measurement. As a result, they were able to increase the sensitivity of the measurement by several order of magnitudes. In their experiment, the value of delta representing the uncertainty of the measurement was reduced to 2.7 times 10 to minus 16. Besides the accuracy of the measurement in tests, another important issue is the validity of Coulomb's law in different circumstances, for example for different ranges of the distance. Various tests were able to demonstrate the validity of Coulomb's law with the accuracy of 10 to minus 9 in the range between a few millimeters up to a few centimeters. In general, experiments can confirm that Coulomb's law is valid in the range between 10 to minus 15 meters up to a few kilometers, and we do not need to rely on theory for the proof. Although the sensitivity of the measurements highly depends on the distance, and only a lower accuracy can be achieved for longer distances. For distances less than 10 to minus 15 meters, the electromagnetic theory cannot be applied due to the vacuum polarization. Therefore we do not expect that Coulomb's law is valid for lengths shorter than 10 to minus 15 meters. In the case of geographic distances or larger length scales, laboratory testing is not available for the validity of Coulomb's law. However, quantum electrodynamics showed photons had non-zero rest mass, and the velocity of electromagnetic waves depended on their wavelength in vacuum if Coulomb's law was not valid for greater distances. Since there is no experimental evidence that the photon has non-zero rest mass, and we could not detect any wavelength dependence of the speed of photons propagating in vacuum, we can conclude that Coulomb's law holds at least with the accuracy of 10 to minus 6 for distances up to few kilometers. We note that Coulomb's law provides the following interpretation of the unit of charge. If 2 point charges of 1 coulomb are placed at a distance of 1 meter in vacuum, then the magnitude of the electric force acting between them is equal to 9 times 10 to 9 newtons. However, the bodies in our everyday environment are not able to attain such amount of charge in excess, due to the repelling force of like charges. Although, the amount of the 2 types of charge that is distributed homogeneously in bodies can reach couple of 1,000 coulombs, only a tiny fraction of these charges can be accumulated as excess charge in these bodies. The amount of their excess charge is about 10 to minus 12 times the amount of the charge present in them. We also note that Coulomb's law determines the electric forces acting between 2 point-like charges in vacuum. If the point charges are interacting in some medium, then the Coulomb force will change and other forces also act between the charges and the medium. In the end of this presentation on electric charge, we will give a summary of the topics discussed here. We started the presentation with the basic phenomena related to electricity in nature, and interpreted the electric forces between bodies as an effect to the presence of electric charge in them. According to this explanation, electric force is an interaction between charges attained by bodies, that is when they are in a charged state. Then we discussed Franklin's classification of electric charge dividing it positive and negative charge, based on the direction of the electrostatic forces acting between them. We concluded that like charges repel each other and opposite charges attract each other. We introduced a simple apparatus called electroscope, which helps us to characterize the electric states of bodies. We give a brief description on golden leaf electroscopes and pointer electroscopes, both using electrostatic forces to detect the presence of charge in bodies. We presented several experiments with electroscopes, where we determined the type of the charge obtained by bodies, and were able to give a semi-qualitative estimate of the amount of charge accumulated in bodies. Electroscopes also helped us to demonstrate the transfer of charge between bodies and the effect of separation of charge. We also classified bodies based on their structural properties permitting or preventing the propagation of charge in them. Materials which conduct electricity, like metals, are called conductors, and materials which do not allow electricity to propagate, like glass, are called electric insulators. Nowadays, the structural properties of matter are explained in atomic physics, therefore we described how electric charge is distributed within atoms. Atomic physics also states that charge has a quantum nature. That is, an elementary charge exists, and any macroscopic charge is always integer multiplies of the elementary charge. We discussed other fundamental properties of electric charge as well, like the invariance of charge stating that the amount of charge is independent of its motion, and the law of conservation of charge saying that the net charge of an isolated system always remains constant. Then we presented Coulomb's famous experiment, in which he used a torsion balance to measure electric forces acting between charged bodies. As a result of his experiment he formulated Coulomb's law, which we discussed here in great detail. In the study of this law we introduced the concept of point charge, which helped us to give a simple description of the electric forces. Coulomb's law states that the magnitude of the electric forces acting between 2 point charges is directly proportional to the product of the amount of the interacting charges, and inversely proportional to the square of the distance between them. The direction of electrostatic force is on the straight line connecting the point charges, and repelling for like charges and attracting for opposite charges. We also discussed that Coulomb's law can be used to describe the interaction between more than 2 point charges if we apply the principle of the superposition of forces. The principle states that the forces between any pair of point charges are given by Coulomb's law regardless of the presence of the other point charges in the system. As a result, the effect on a point charge by a system of point charges is the net effect on the point charge by all the point charges in the system. We introduced the CGS and SI units of charge, like Coulomb and the electrostatic or electromagnetic units of charge, based on either electrostatic interaction or interaction between moving charges. The choice of the unit of charge also determines the form of Coulomb's law and other laws of nature related to electricity and magnetism. Finally, we presented another famous experiment performed by Cavendish, in which he attempted to measure electrostatic forces with high precision. We also enlisted several experiments carried out in the last 200 years testing the inverse square law, and we concluded that the relative error in such experiments are already reduced to the order of 10 to -16. These experiments test the validity of Coulomb's law as well. Laboratory tests on large distances showed that the inverse square law holds with extreme precision. On subatomic length scale quantum electrodynamics is applied instead of electromagnetic theory, where the laws of quantum mechanics are used to describe the interaction between particles carrying charge rather than Coulomb's law.